There is a moment in every science fiction story where someone does something that used to be impossible, and afterwards the world never quite snaps back into place. For Mars, that moment is not a distant fantasy anymore. Somewhere in your lifetime, people will walk up a tower of stainless steel, strap in above a lake of methane and oxygen, and ride a controlled explosion away from Earth on a one-way trip. They will not be test pilots in silver suits. They will be engineers, teachers, cooks, retirees, maybe someone very much like you. The ticket will promise adventure and a fresh start on a red world. Hidden in the fine print will be a stranger price. Your body, your brain, even your DNA will not come home the way they left. So what actually happens to you when you say yes to that ticket and trust a shining steel rocket to carry you away from the only planet you have ever known? To understand that price, we have to start with the machine that makes the offer. SpaceX built Starship as something very different from the delicate white pencils we associate with Apollo or the Space Shuttle. Think of a two-part system taller than most skyscrapers. At the bottom sits the super-heavy booster, nearly 70 meters of fuel tanks and plumbing feeding more than 30 Raptor engines, each one a compact furnace that mixes liquid methane with liquid oxygen and hurls the exhaust downward with staggering force. On top of that booster sits the spacecraft that keeps the name Starship, about 50 meters tall with a 9-meter diameter body and a pointed nose. The skin is not a fragile composite. It is a version of stainless steel, more like a polished industrial tank than a luxury product, chosen because it can take heat up to well over 1,300 degrees without warping, and because it is cheap to build in large numbers. That choice reveals the real plan. This is not meant to be one glorious flag-planting mission that flies once. Stainless steel is easy to weld, easy to roll into cylinders, and relatively inexpensive compared to exotic carbon fibre. That lets you imagine a fleet of them, launched, landed, refueled, and launched again, like a rough and ready airline that happens to leave the planet. Inside the upper stage, behind that shiny hull, is a mostly hollow volume that can carry around 100 tons of payload. It is a vast metal tube 18 meters high, wide enough to swallow small houses or a cluster of satellites. For early missions, the payload will be cargo and test hardware. For Mars, it will be people. The company has been remarkably clear about that. The big empty volume is a future habitat, not just a freight container. So picture this sometime in the middle of this century. Your phone buzzes with an acceptance notice from a Mars colonization program. You have passed the health checks, the psychological screens, the skill tests. Months later, you arrive at a coastal launch site that looks half like a rocket range and half like a futuristic port. The air smells of salt and fuel. Somewhere beyond the fences, a Starship stands on its booster, a silver needle against the sky. Around you gather roughly 100 other passengers, the number the company thinks it can fit without turning the ship into a flying sardine can. You hear snatches of conversation in different languages, see nervous jokes, quiet tears, stares out toward the ocean. On an airplane, you can tolerate an annoying seatmate because the worst case is a long, uncomfortable day. Here, these strangers are the people you will eat breakfast with for half a year. They will see you exhausted, elated, sick, bored, lonely. There is no stepping off at a layover if it turns out you do not get along. You file through medical checks and final briefings, learning yet again that there is no emergency hospital midway, no rapid rescue if someone has a stroke or an appendix burst. The safest medicine is prevention, which is why you have been training for months to arrive as healthy as possible. Finally, the day comes when buses roll you out to the pad. Up close, the booster feels impossibly large, like a metallic cliff with engine bells hiding under its skirt. Elevators and elevators within elevators lift you through access towers and airlocks until you arrive in a long cabin lined with seats. Harnesses cross your chest. A flight surgeon checks your straps and your heart rate. Outside, the countdown voice ticks downward. When the engines light, the entire world seems to turn into vibration and noise. You feel your weight multiply as the booster paws thrust into the ground and the ship claws upward, pressing you back into the chair, harder than any roller coaster you have ever ridden. Launch is short, perhaps 9 minutes from ground to orbital velocity, but your body notices every second. At a planned moment, the booster shuts down and separates, falling back toward Earth, where it will attempt to flip, burn, and land for reuse on a pad or ship downrange. You do not see that. You feel a brief sense of tumbling, and then another set of engines ignites under your feet as the Starship itself takes over. The cabin shakes again, then gradually smooths as air thins and drag fades. You pass the invisible boundary that pilots call the edge of space, and keep going, accelerating until your speed is so high that if the engines turned off and you did nothing else, you would miss Earth entirely and fall around it indefinitely. Finally, the thrust cuts out. For the first time, you are truly falling together with the ship, not through air but through emptiness. Your weight seems to vanish. A pen that slips from someone's fingers does not fall. It hovers beside their hand and drifts away, slow and surreal. At some point, straps release, and the crew invites you to stand. Standing is the wrong word. You push lightly against the seat and float upward, trying to remember that any sudden movement sends you careening in the opposite direction. This is the environment you will live in for months. Plans for Starship imagine multiple levels inside the pressure hull, divided by floors and walls much like a narrow apartment building. At the lower level are bunk areas, rows of small cabins that you share with one or two other people. They are barely large enough for sleeping bags, a few personal items, and perhaps a tiny viewport. Above that sits a common area with handholds everywhere, where people can eat, talk, play zero-gravity games, and stare out large windows when the design allows. Somewhere nearby are workstations and terminals, where you monitor systems, write reports, or talk to family back on Earth, with signals already starting to lag as the distance grows. Exercise equipment is bolted down across one wall. There are resistance bands, stationary bikes with harnesses, treadmills with bungee cords that pull you down to simulate weight, and maybe newer machines designed specifically for partial gravity conditioning. On the International Space Station, astronauts set aside roughly 2 hours a day to fight muscle loss and bone thinning. On a 6-month voyage to Mars, you are expected to do the same. Often you will do it when your mind is tired and you would rather float in the window bay, watching the shrinking blue marble behind. But skipping too many sessions is not an option. In weightlessness, your body assumes gravity is gone forever. It starts reallocating resources and redesigning itself for a new normal. If you arrived on Mars or came back to Earth after months of drifting without exercise, standing up could become a serious challenge. The mundane details of living become science experiments of their own. Water does not pour, it clumps, clings, forms lazy spheres that wobble and drift. That means showers are impractical. On current missions, astronauts use rinse-free shampoos and wipe themselves down with damp cloth. You do the same, carefully wringing out just enough liquid from sealed bags so droplets do not go wandering into air filters. Toilets are another engineering compromise. Without gravity, waste does not conveniently fall away. Facilities use carefully directed airflow and vacuum systems, and you strap yourself to a seat so nothing and no one floats unexpectedly in a direction they should not. Food is chosen not just for nutrition, but for behavior in microgravity. Crumbs can clog instruments, loose salt or pepper becomes a cloud of stinging dust. Seasonings arrive dissolved in liquid, and meals are often vacuum-packed and rehydrated. Somewhere deep in the ship, a set of tanks and filters quietly handle every drop of water that passes through every body, reclaiming, cleaning, and sending it back into circulation. Knowing that intellectually is different from taking your first sip of recycled coffee. It is one of many moments where you have to decide what you are willing to accept to live off Earth. Sleep does not honour day and night in the way you are used to. The ship spins around the sun, not around Earth, so there is no regular pattern of sunrise and sunset outside a window to orient your body clock. Light cues are artificial, programmed into the interior to mimic a 24-hour cycle. You zip yourself into a sleeping bag attached to a wall so you do not float through the cabin in the dark and bump into equipment. Some people sleep better this way, feeling strangely freed by the lack of pressure points. Others lie awake, mind racing, feeling ungrounded in the most literal sense. You might wonder, on the 20th or 50th night of that strange floating sleep, whether your sense of home is slowly detaching itself from the planet behind you and attaching to the humming metal habitat around you instead. that silent shift is part of the ticket price too. All the while, an invisible hazard seeps through the hull. Between you and the sun, there is no longer a thick magnetic field to deflect charged particles, no deep blanket of atmosphere to absorb bursts of radiation. The ship itself is designed with shielding in mind. Certain walls are thicker, tanks of water or fuel are arranged strategically to soak up some of the bombardment. Within the living volume, you know the locations of storm shelters, small compartments with extra layers of material and often surrounded by those same water tanks. When space weather centers detect a solar flare or coronal mass ejection heading your way, alarms sound, and you and your fellow travelers gather in those cramped safe rooms for hours, sometimes longer, waiting for the worst of the particle storm to pass. Conversations go quiet. You can feel the reality of space as a hostile environment in every square meter of packed bodies and hurried breathing. Even without flares, the background drizzle of cosmic rays and solar particles adds up. Every day in transit, you are receiving more radiation than you would on the ground, even more than on a commercial flight. Doctors and engineers calculate expected doses over the mission and compare them with lifetime limits for astronauts. The numbers are sobering. Estimates for a full round trip to Mars, including time on the surface where there is less atmosphere than Earth, suggest a total exposure near or even above current career caps for radiation workers in space. In crude terms, you get one big adventure before the risk becomes too high to justify another. That is one reason why mission planners talk seriously about older crews for early Mars trips. If you are already in your 50s or 60s, the absolute increase in lifetime cancer risk may be judged more acceptable than for someone who is 25. Meanwhile, gravity, or the lack of it, is quietly rewriting your biology. In the first days, your face puffs up, eyes redden slightly, and your sinuses feel congested. Blood and other fluids, no longer pulled down toward your legs, redistribute evenly. Your heart, which has spent decades pumping uphill against gravity, suddenly finds the job easier and overshoots. It takes a while for your cardiovascular system to adjust. Over weeks and months, your spine relaxes and elongates. Astronauts have reported growing by as much as a couple of centimeters in height during long stays in orbit. That sounds amusing until you remember that the tissues involved were not designed for this new arrangement, and that the compression when you later return to a gravity field can cause back pain or worse. Bones that normally bear weight begin to lose density. Muscles that stabilize your posture shrink. Even your inner ear, responsible for balance, has to relearn what up and down mean. Deeper still, down in the microscopic machinery of your cells, the environment begins to leave signatures. NASA once ran a remarkable natural experiment with identical twin astronauts. One spent almost a year on the International Space Station, while his brother stayed on Earth. Their genetics at birth were the same. After the mission, when blood and tissue samples were compared, scientists found that patterns of gene activity, the on and off switches that control which parts of the DNA are being read, had shifted. Some changes reversed within months after landing, others did not. A small but noticeable fraction of gene expression differences remained altered long after the returning twin was back under normal gravity and shielded by the atmosphere again. The study was not perfect, and it involved a single pair of people, but it reinforced an unsettling idea. Time in space does not just stress your body, it coaxes your cells into new states that may not fully go away. On Mars, gravity is lower than Earth, about a third of what you grew up with. The planet has no global magnetic field, the air is thin and cannot block radiation the way our sky does. So when you eventually drop into orbit around that red world, and the ship begins its entry, your tissues are already adapted to microgravity, and your DNA may be expressing itself in slightly different patterns. Starship reorients into a belly flop configuration, its broad steel body presenting a huge surface to the Martian atmosphere. Control surfaces on its sides move constantly, trading angle and drag, bleeding off kinetic energy through controlled chaos. The heat on the outside climbs, but the steel holds. Near the ground, the engines relight, swinging the ship into a vertical posture and easing it onto a landing pad near a cluster of domes and structures that will be your new neighborhood. When the hatch finally opens, you do not step directly onto Martian soil. You move through pressurized tunnels into habitats where the air has been built molecule by molecule and the pressure is controlled by valves and computers. Somewhere nearby, another starship is parked that has been sitting for months, patiently making fuel from the local carbon dioxide and water ice, splitting molecules and liquefying propellants the way a tiny chemical factory would on Earth. Refueling and self-sufficiency are part of the grand economic plan. For you, the effect is more intimate. You take your first real breath of off-world air, plant your feet on a floor that pretends to be down again, and realise that the person doing these things is not quite the same person who boarded at Earth. Your muscles, bones, arteries and genes have all been bent by 6 months of falling toward a different planet. Somewhere in the background, there is already work underway on engines and ships that might one day cut that travel time dramatically. Before we get to that future, it is worth asking one simple question. How much change in your body and your identity are you willing to accept for a chance to call another world home? The strange thing is that even before anyone steps onto Mars, the future of that journey is already limited by the way we shove ships away from Earth. If you strip away all the shiny branding and national flags, a rocket is really just a very dramatic way to obey one simple rule of the universe. Momentum is conserved. If you want to go one way, you have to throw something else the other way. That is it. The balloon that flies across a room when you let it go is doing rocket science. Air inside rushes out in one direction. The balloon moves in the opposite direction. The total momentum stays balanced. What we have done with enormous metal cylinders is take that same trick and scale it up until the exhaust is so hot and so fast that the only way to see it clearly is in high-speed footage. The core of chemical rocketry is simple enough that your high school physics teacher could sketch it on a board. You store fuel and oxidizer in tanks. You mix them and burn them in a chamber so the reaction produces enormous amounts of hot gas. That gas is squeezed out through a nozzle, shaped so that the flow expands and accelerates in just the right way to produce thrust. Push enough mass out fast enough and the rocket rises. Make the exhaust faster and you get more momentum for every kilogram of propellant. Throw more mass out and you get more momentum as well. That sounds like a clean path to better performance. Either push stuff out faster or push more stuff out. In reality, both options run into painful limits. The faster you want to accelerate your exhaust, the hotter and more demanding the engine becomes. You need stronger turbopumps, more exotic materials, better cooling channels, more precise control. All of that adds mass. To throw more mass out, you fill bigger tanks. Bigger tanks weigh more when empty. They need bigger engines, stronger structures, thicker walls, more insulation. That adds even more mass. The rocket equation hides behind all of this. It says that to produce a particular change in speed, the amount of fuel you need grows in a way that is not friendly or linear. Each extra kilometre per second costs more and more propellant. By the time you push toward escape velocities that let you leave Earth entirely, you are stacking fuel on top of fuel just to push more fuel. You can see this in classic heavy lifters. The mighty Saturn rockets that took humans to the moon held millions of litres of propellant in their lower stages. Almost all of that mass was burned in just a few minutes at liftoff, not to send a city into space, but to place a relatively small payload on a path toward the moon. The core stage of a modern super heavy booster similarly guzzles vast amounts of methane and oxygen just to reach orbit. When the tanks are empty, that is it. Chemical rockets cannot sip fuel, they gulp it. Once the burn is over, the engine falls silent. The only way to speed up later is to have carried even more propellant, which made your rocket heavier, which required even more propellant. You can feel the vicious circle tightening. This is where space engineers began to wonder whether they were pushing the wrong part of the equation. What if, instead of thinking of rockets as brief, violent bursts of thrust, we treated them like patient engines that whisper instead of roar? If momentum depends on the mass of the exhaust multiplied by its speed, you can trade one term for the other. Rather than throwing out heavy molecules slowly and wasting most of the energy as heat, you could throw out very light particles at incredibly high speed. You would not get much push at any given moment, but if you keep that push going for months or years in the vacuum between planets, the results can be astonishing. That idea leads directly to ion engines. Ion engines start by taking a gas and turning its atoms into charged particles, little beads of matter missing electrons. Electric fields and magnetic fields are very good at grabbing charged particles and flinging them around. Inside an ion thruster, grids or electromagnetic structures accelerate those ions out the back of a spacecraft at tens of thousands of meters per second. Compared with traditional rocket exhaust, that is like the difference between a garden hose and a pressure washer. For every kilogram of xenon or other propellant you carry, you get many times more momentum. Engineers call that better specific impulse, which is a fancy way of saying you get far more change in speed per unit of propellant than a chemical rocket can ever hope to achieve. The trade-off is that the push at any moment is tiny. So tiny that if you could stand on the thruster while it fired, you would barely feel it. Think of the weight of a sheet of paper resting on your hand. That is the order of magnitude of force some early ion engines produced. On the ground, that would be useless. Against the pull of Earth, such a whisper of thrust would never lift you even a millimeter. In the near-perfect vacuum of deep space, with no air drag and no gravity well to climb out of, that gentle, constant push shines. It does not have to win in a sprint, it wins in the marathon. Let an ion engine run for months, and the speed it can reach slowly climbs past what a chemical rocket can deliver in a brief blaze of glory. We have already tested this in the real sky, not just on whiteboards. Experimental spacecraft with ion propulsion have visited asteroids and comets, looping out on long trajectories and gradually reshaping their orbits. Some orbit-raising and station-keeping systems on satellites use electric propulsion to nibble against drag, firing almost continuously for years at a time, holding a platform steady over a given point on Earth. There have been Russian and Soviet satellites that let their electric thrusters run for thousands of hours without serious trouble, proving that this is not just a laboratory toy. You might find it oddly satisfying to imagine a spacecraft slowly but relentlessly building speed, day after day, until its final velocity dwarfs the short burst sprint of the old-style rockets that first launched it. Yet there are reasons why every launch pad on the planet still rests under chemical thunder. Ion engines have serious practical problems. First, they need electricity, and a lot of it compared with what tiny control systems require. A gas molecule in an ion thruster is essentially your battery. The exhaust speed is tied to how much electrical energy you can feed into the plasma. On a probe near Earth or Mars, you can spread out big solar panels and drink sunlight. Farther out near Jupiter or beyond, sunlight is too weak. You would need compact but powerful nuclear power sources to keep an ion engine fed. Right now, we are still cautious about how we launch and operate nuclear reactors in space. Second, the charged particles that make ion engines work are also very good at eroding the surfaces they touch. The grids in some designs are slowly sandblasted by high-speed ions. That is why some newer concepts try to do away with metal grids entirely and rely on magnetic fields to steer and accelerate plasma. Third, some of the best propellant candidates are rare and expensive. Xenon is a noble gas that behaves beautifully in many thrusters, but it is chemically inert and not terribly common. Its price per kilogram is high. A fleet of large ion-driven freighters would need a propellant supply chain very different from what we use today. Designers are experimenting with gases that could be harvested in orbit or even skimmed from the edge of Earth's atmosphere, trying to imagine engines that can refuel themselves by dragging in trace molecules and throwing them out again. That self-feeding idea shows up in helicon thrusters and in other plasma concepts that switch between different modes of operation. A helicon device uses radio waves to create a dense plasma in a magnetic bottle. Because there are no grids inside the exhaust path, there is less hardware to erode. There is a vision in which fleets of these engines breathe from the thin upper atmosphere, converting a slow death spiral into almost indefinite life. It sounds like magic, but at root, it is still the same momentum game. The craft collects tiny bits of matter, accelerates them electrically, and pushes against them. In some testbeds, these devices have run for very long times, hinting at a future where satellites can hold their orbits far longer than they can today. Then there is the showy cousin of ion engines, the variable specific impulse magnetoplasma rocket, often shortened to a friendlier name in news stories. You can think of it as a kind of plasma blowtorch. It takes a neutral gas and uses radio frequency waves to strip away electrons and create plasma, Then it uses more energy and strong magnetic fields to heat that plasma to nearly 1,000,000 degrees Celsius inside the engine core. At those temperatures, the particles are racing around like a superheated gas in a star. The engine channels them down a magnetic nozzle and releases them at incredible speed. By adjusting how much power it puts into heating versus how much mass it pushes, the engine can trade between high thrust and high efficiency. On paper, a large version of this plasma engine powered by a nuclear reactor could send humans to Mars in a matter of weeks instead of months. You do not coast ballistically on a carefully timed Hohmann transfer. Instead, you accelerate almost half the way there, then flip and decelerate almost half the way back down, riding a continuous curve of thrust. That would not just be convenient, it would radically cut the time your body spends unshielded in deep space. Less radiation, less microgravity, less boredom. It is the kind of idea that makes science fiction fans sit up and say, yes, that is what we have been waiting for. The problem is that the engine is an energy addict. Heating plasma to star-like temperatures takes serious power. The prototypes that have run on Earth have been hooked to grid-based supplies in laboratories. Scaling them to a space-ready system means carrying a compact power plant on board that can output megawatts steadily without melting itself. Solar panels would need to be vast and unwieldy. Nuclear reactors in orbit bring their own engineering and political challenges. So for now, plasma engines stay mostly in the future column, a technology we keep returning to in studies and small-scale tests, waiting for the rest of our infrastructure to catch up. It is easy to hear about these advanced engines and imagine that we will flip a switch one decade and suddenly all rockets will be sleek, plasma-powered ships. Reality will be messier. Chemical boosters are very good at one thing that electric thrusters are terrible at. They deliver a huge punch in a short time. That is exactly what you need to climb out of an atmosphere and fight gravity. Electric engines are very good at another thing that chemical boosters are terrible at. They deliver gentle but efficient push over very long durations. So the future likely belongs to hybrid missions, where a chemical stage gets you off the ground and into orbit, and some form of electric drive takes over in deep space. Imagine a Mars journey where you ride a launch that feels familiar from the era of Starship. Once in orbit, your ship docks with a transfer stage that is basically a flying power plant wrapped around an electric engine cluster. Solar wings unfold like city blocks of glass or thin film, or a compact nuclear reactor warms up and feeds current into magnet coils. The light goes from orange chemical fire to invisible electromagnetic fields. Acceleration is barely noticeable, perhaps just enough to simulate a gentle artificial gravity if the ship rotates slowly. Day after day, the numbers on the navigation board climb, speed relative to Earth, travel time remaining, estimated radiation dose saved compared with a slow cruise. If you picture yourself watching those readouts, you can feel why this matters not just as engineering, but as a human experience. There is a deeper question under all of this. The moment we move from rockets that burn through their fuel in minutes to engines that sip energy over years, we change what kinds of missions are possible. Suddenly, asteroid rendezvous, outer planet tours, and even missions into the distant Kuiper belt become more than one-shot heroic flybys. Ships can brake, turn, survey, and move on. Cargo vessels can deliver heavy equipment ahead of humans. Robotic scouts can be retasked mid-flight to chase newly discovered objects. The shape of our presence in the solar system begins to look less like footprints on a bare beach and more like shipping lanes connecting many ports. The physics is unforgiving. Conservation of momentum does not negotiate. Yet within that simple rule, there is an enormous design space we have barely explored. Somewhere between the brute force of chemical fire and the whisper of ion beams lies the combination that will open the rest of the solar system to routine travel. The interesting part is that the decision about which combination we build is not just a technical one. It is also about money, risk, profit, and prestige. Before these new engines can really leave their mark, we have to watch who is racing to fund them, what stories they tell the public to justify the cost, and whose dreams they intend to serve when the first quiet interplanetary freighters finally light up their drives. Look at who is climbing the launch towers now. For most of spaceflight history, the story was simple. States pointed rockets upward. Agencies with acronyms and flags sent carefully selected crews into orbit in the name of national pride and science. If you were not born in the right country, with the right training and the right passport, the chance of leaving Earth was effectively zero. That picture is starting to crack. Private logos now share rocket fairings with national symbols, and some of the loudest voices talking about off-world futures belong not to presidents, but to tech billionaires. In the early 2000s, that shift was still more dream than delivery. Government programs were still the only way for humans to reach orbit. Yet there were a few strange projects on the horizon, funded not by space agencies, but by rich entrepreneurs and prize money. One of them was a sleek little craft built by a company called Scaled Composites. Their goal was not a government contract. They were chasing a $10 million pot of money called the Ansari X Prize, offered to the first private team that could fly a reusable crewed vehicle to the edge of space twice inside 2 weeks. The rules required them to carry the equivalent mass of 3 people, above a boundary that many aerospace experts accept as the edge of space, roughly 100 kilometers above sea level. That imaginary line is named after a scientist who tried to calculate where aerodynamic lift stops working and orbit becomes the only way to stay up. Instead of going straight up like a traditional rocket, the Scaled Composites team chose an air launch design. A big carrier aircraft nicknamed White Knight hauled their rocket plane high into the sky. There, the smaller craft, called Spaceship One, dropped away, lit its hybrid rocket engine, and arced up into thin blue, then dark. To passengers on board, the experience would have felt like a strange, elongated roller coaster. First, there is the smooth but powerful climb under the carrier aircraft. Then, a brief moment of freefall as the rocket plane releases. Then, an almost chair-shaking surge as the rocket fires, pressing you into your seat as the horizon falls away and the sky turns ink black. Near the top of the trajectory, engine off, everything outside the windows has an unreal quality. There is still a faint blue glow along the curve of Earth, but above you there is only darkness. Inside the cabin, straps loosen and you float. Loose objects drift. Your body tries to decide if this is frightening or wonderful. That flight path was not an orbital mission. After only a few minutes at the top, gravity wins back control. The craft begins to fall, tumbles into a feathered configuration that creates drag and stability, then glides back to a runway like a futuristic glider. From takeoff to landing, the whole experience lasts around 2 hours. It is an intense thrill ride, not a journey to a new world. Yet when Spaceship One won the prize in 2004, it proved that a small company could put people into space-adjacent territory without a state budget. Among the people watching that success was Richard Branson, founder of the Virgin brand, who saw not just an engineering feat, but a business model. Branson partnered with the builders to create a new company focused on space tourism. The basic idea was simple. If you can make that up-and-down adventure safe and routine, there are customers who will pay enormous sums for it. Virgin Galactic built a bigger carrier plane called White Knight 2, and a follow-on rocket plane called Spaceship 2. The ticket price they announced hovered in the hundreds of thousands of dollars, far beyond anything most of us could afford, yet within reach for wealthy thrill seekers and status-hungry travellers. For that money, you would get training, a custom flight suit, bragging rights, and a few precious minutes of free floating weightlessness above the world. From a distance, it is easy to roll your eyes at billionaires selling a few minutes of microgravity to other rich people. Yet if you step back and look at the hardware, you can see the glimmer of something else. Every test flight that proves the design gives engineers more data about re-entry, control systems, composite structures, and rapid reuse. The carrier aircraft and rocket plane have to be turned around and flown again and again. Maintenance routines are refined, safety margins and retested. Even the interior design of the cabin, with its edges softened and handles placed exactly where disoriented passengers might reach, feeds back into a body of knowledge about how to move ordinary humans through extraordinary environments. While Virgin focused on winged vehicles and airport-like operations, another billionaire was taking a more traditional rocket approach. In the year 2000, Jeff Bezos, already wealthy from building an online retail empire, quietly founded a company with a simple mission statement about building a road to space. For almost a decade, this company, Blue Origin, stayed mostly in the shadows, testing engines and hardware without splashy public launches. Its founder preferred long-term thinking. When he did speak, he painted a picture of millions of people living and working in space, with heavy industry moved off-world so that the surface of Earth could be preserved as a garden. Blue Origin's first big tourist-facing machine is New Shepard, a vertical launch rocket named in honor of the first American astronaut to reach space. The vehicle consists of a booster topped by a capsule with large windows. It goes straight up and straight down. On a typical flight, the booster lifts the capsule past the notional edge of space to altitudes just over 100 kilometers. During that coast phase, the capsule separates and passengers unstrap to experience a few minutes of weightlessness as Earth curves dramatically beneath them. Then the capsule falls back down, deploying parachutes for a gentle landing. Meanwhile, the booster uses its own engine to reignite and land propulsively on a pad. The flight is short, roughly 10 minutes from launch to touchdown. Tickets are again priced in the hundreds of thousands. Blue Origin has already flown its founder, some paying customers, and invited guests. To critics, this can look like a vanity project. To supporters, it is a testbed for reusable vertical rockets and human-rated capsules. New Shepard has flown multiple times, landing its booster repeatedly, which helps build the confidence needed for more ambitious vehicles. On the drawing board, and in ongoing development, is a much larger rocket called New Glenn, designed to reach orbit, carry heavier payloads, and serve as a workhorse for satellites and maybe one day crewed missions. Both Virgin Galactic and Blue Origin frame their projects as steps toward making space access cheaper and more common. They talk about opening space to everyone, even though the early flights are realistically open only to wealthy clients. This can sound cynical, yet in aviation history, early commercial flights were also expensive toys for the well-off. Over time, competition, technology, and scale drove prices down. Whether that pattern repeats for suborbital tourism is an open question. We can ask a harder one. Are these companies really trying to democratize space? Or are they building brand empires in the sky and securing early control over very profitable launch lanes? Into this evolving landscape strides Elon Musk and SpaceX, with a style and strategy that feels very different. Where Virgin and Blue Origin started with suborbital joyrides, SpaceX went straight for orbital services and cargo. They built the Falcon series of rockets and designed them from the start with reusability in mind. The Falcon 9 first stage now lands routinely on drone ships or pads, a move that slashes the effective cost per launch. Instead of throwing away a perfectly good engine stack into the ocean every time, they bring it back, refurbish it, and fly it again. The revenue comes not from tourists, but from contracts to loft satellites, resupply the International Space Station, and eventually ferry crew. That difference in business model matters. SpaceX makes money by becoming a freight company and a taxi service for space agencies and satellite operators. Each launch that delivers a commercial communications satellite, a batch of internet satellites, or a cargo capsule to orbit pays for more development. Space tourism under this model is not the first product. It is something that can be layered on top later, when the basic transportation system is mature. You can imagine a future in which a Starship variant is outfitted with cabins for passengers who want a few orbits and a view, while other Starships haul heavy cargo or fuel between Earth, the Moon, and Mars. All three billionaire-backed ventures share one thing. They operate within a legal and political environment that was designed when only nations went to space. The foundational treaty that still shapes our actions beyond Earth says that no country can claim sovereignty over the Moon or a planet by planting a flag. It forbids placing nuclear weapons in orbit and insists that space exploration should benefit all humankind. It says less about private resource extraction or tourism. As companies build hardware that can actually land, dig, and transport, governments are quietly passing national laws that grant their firms rights to use resources they extract, or that set liability rules for private launches. That raises uneasy questions. If a company builds a refueling depot in lunar orbit, who sets the price of propellant? If one nation grants extensive rights to its corporations to own and sell lunar resources, while another does not, whose interpretation of space law wins when there is a dispute? If orbit becomes crowded with tourist flights and mega constellations of satellites, who manages the traffic? Regulators in the United States and other countries are already experimenting with light touch oversight that encourages innovation while trying to keep public safety and national security concerns in view. They have to decide how much risk passengers can freely accept and where the state must intervene. For you as a future traveller, or even as a citizen on the ground, the interesting part is how these business and legal decisions will shape what is possible. If tourism is the main driver, vehicles will be optimised for cabin experience, big windows, and memorable views. If cargo contracts dominate, rockets will be optimised for cost per kilogram and reliability. If lunar mining and industrial operations start to generate serious revenue, infrastructure will shift toward making cislunar space a kind of high ground where propellant, metals, and manufactured parts move between depots. Each path leads to a different kind of sky. You might ask yourself which version of the future you are actually being sold when you watch another glossy promotional video of a smiling family floating in a cabin. There is also the question of competition. Governments once used space races to demonstrate technological superiority. Now companies use rocket milestones to attract investment and talent. A record flight, a flawless landing, or a new altitude reached can send share prices up and trigger a wave of funding. The pressure to be first can drive rapid innovation. It can also tempt organisations to cut corners. When the product is a social media app, a rushed launch can be annoying. When the product is a rocket full of people, the stakes are the lives of passengers and crew. In this environment, thoughtful regulation and transparent safety practices are not just red tape, they are essential to building trust. At the same time, the presence of multiple capable launch providers introduces a kind of healthy redundancy. If one company suffers a serious accident and has to ground its fleet, others may be able to continue critical missions. Satellites can still be launched, supply runs to space stations can continue. Over the long term, this diversity of actors could make humanity's foothold in space more robust. It could also mean that values and priorities differ from one orbital hub to another. A research station serviced mostly by agencies might feel very different from a hotel in orbit owned entirely by a private brand. Standing back from the timelines and hardware, we can see a simple but powerful pattern. What began as a purely national endeavour is becoming an industry, with all the complexities that entails. Marketing teams now sit alongside engineers, crafting narratives about adventure and inspiration. Legal departments comb through treaties. Investors study projected launch cadences and payload manifests. The same forces that once shaped shipping routes, airlines, and internet infrastructure are now starting to shape who goes to space, why, and on what terms. You and I are watching the opening of a new economic frontier, one rocket test at a time. Yet a frontier is not really open just because you can reach it. For space to become woven into daily human life, not just as a distant spectacle, it has to be connected. Every tourist cabin and industrial module, every rover and lab on a moon or planet, depends on a fragile lifeline built out of signals. Those signals cross millions or billions of kilometers of empty darkness and arrive as faint whispers of radio noise on giant antennas back on Earth. As rockets become more capable and missions more ambitious, that invisible network becomes the real backbone of exploration. And that leads us to a quieter, but equally revolutionary question. How do we talk to all these distant machines and habitats without losing their voices in the cosmic background? The backbone of our presence beyond Earth is not the rockets that leave glowing trails, it is the faint whispers that come back. Every photo you have ever seen from Mars, every close-up of a comet or moon, every reading from a distant probe, travelled home as a delicate pattern of radio energy that could easily be lost in the noise of the universe. On your phone, a lost bar of reception is annoying. Out past Mars, losing connection means a billion-dollar machine goes silent in a permanent night. So engineers built something that looks almost like science fiction in its own right, a planet-sized ear called the Deep Space Network, whose only job is to listen. Imagine a dry desert in California, hills outside Madrid, and scrublands near Canberra in Australia. In each of those places, far from big cities and their radio chatter, sit clusters of enormous white dishes. Some are as wide as a 7-story building is tall, with surfaces polished so precisely that they can focus radio waves that have spread and faded over hundreds of millions of kilometers. This triangle of sights gives Earth something close to a continuous ear. As the planet spins, at least one of these complexes always has a clear view of almost any point in the sky where a spacecraft might be. When NASA first built this system, the idea was to avoid the tangled mess of each mission erecting its own antennas. Instead, all deep space missions would share one global network. Voyager spacecraft heading for Jupiter and Saturn, early lunar orbiters, and interplanetary probes all took turns using the same giant dishes. When you see those iconic images of a storm on Jupiter or a thin ring of Saturn, remember that the raw data arrived at Earth as a whisper on those antennas, weaker than the signal from a light bulb on the Moon, buried in background noise and then teased out by clever electronics. The reason the dishes are so large is simple physics. Radio waves spread out as they travel. Their intensity drops off roughly with the square of the distance. Double the distance and the power gets 4 times weaker. By the time a signal has crossed the gulf from Mars or beyond, it is unimaginably faint. A dish works by collecting those weak waves over a large area and focusing them onto a detector. Bigger area means more signal. But you cannot just keep building larger and larger single antennas forever. They become hard to engineer, hard to move, and very expensive. At some point, you reach a practical limit. The Deep Space Network adapted by adding more dishes and learning to link them together electronically, a bit like combining the eyes of several telescopes. If you phase the signals correctly, many smaller antennas can act like one larger ear. Upgrades over the years have added new frequency bands, cleaner amplifiers, and more powerful transmitters that send instructions outward. The network has become a shared utility that spacecraft designers depend on. A new Mars rover does not have to build its own global listening system. It just has to be compatible with the network that already exists. That shared system is under enormous pressure. Look at the sky on a mission schedule and you will see why. At any given time, Mars alone may host orbiters from multiple agencies, landers on the surface, and rovers crawling through craters. Further out, there are probes at Jupiter and Saturn, asteroid missions, solar observatories far from Earth, and testbeds exploring strange orbits. Each one wants time on an antenna to send back images, spectra, health reports, and sometimes software updates. The Deep Space Network schedules look like a tightly packed puzzle, with missions taking turns, handing off between dishes as Earth spins, and accepting data rate compromises when demand is high. For you sitting at home, the result is that most spacecraft do not stream data the way you stream a movie. A rover on Mars may send back a handful of high-resolution images in a day, plus compressed sensor readings and housekeeping information. When the New Horizons spacecraft flew past Pluto, it gathered a treasure trove of data in a single burst of time. But the connection home was so limited that it took many months for all that information to trickle back across billions of kilometers. Imagine taking the most important photographs of a lifetime and then waiting for nearly a year to see them in full detail. There is another limiter that no amount of hardware can erase. Light has a finite speed. Radio waves, which are a form of light, share that speed limit. The distance to Mars changes as both planets orbit the Sun. At its closest, the one-way travel time for a signal is several minutes. At its farthest, it can be more than 20 minutes. That means you cannot joystick a rover the way you would a remote control car. By the time your command arrives, the situation on the ground has changed. By the time the rover reports back, you are reacting to the past. Farther missions suffer even longer delays that stretch into hours. As a result, deep space explorers have to be smart enough to act locally, with only general instructions from Earth. Engineers have stretched the radio tools impressively. They have moved to higher frequency bands that can carry more data, designed error-correcting codes that squeeze reliable bits out of low signal strengths, and integrated arrays of dishes to act together. Yet the basic limits are still there. At some point, if you want to send more information through the same window of time, you need a different kind of beam. That is where lasers enter the story, not as weapons from a science fiction movie, but as communication tools. A laser is basically light that has been told to behave. Instead of spreading wildly across frequencies and directions, a laser emits a very narrow beam at a specific colour. That beam can be pointed and focused with far greater precision than a broad radio transmission. Pack information onto that narrow shaft of light, and you can push many more bits per second toward a receiver. The same physics that makes a laser pointer visible across a stadium can, when scaled up carefully, make a space laser link carry far more data than a radio link that uses similar power. NASA and other agencies have already run experiments to test this idea beyond the lab. One early demonstration, riding on a small lunar mission, used lasers to send data between a spacecraft orbiting the Moon and ground stations on Earth. The experiment managed to push information at rates many times higher than comparable radio systems. More recently, a technology demonstration mission in geostationary orbit has been testing laser links between space and Earth over long periods. Its job is not to explore a planet or moon, but to study how an optical communication system behaves through real clouds, turbulence, and day-night cycles. The most ambitious tests yet are starting to appear on deep space missions. One spacecraft heading for a metal-rich asteroid carries a small optical terminal that aims an infrared laser back at Earth, trying to maintain lock over tens of millions of kilometers. On the ground, specialized telescopes equipped with sensitive detectors sit ready to catch those photons as they arrive, distorted by the atmosphere, yet still carrying a rich stream of data. If these tests succeed, they will prove that a spacecraft can use lasers to send more science per minute, effectively widening the pipe between itself and the planet. Of course, nothing is free. A narrow laser beam is a double-edged sword. It carries information efficiently, but it must be aimed precisely. Pointing errors that would be trivial for broad radio waves can cause a laser to miss its target entirely. The atmosphere adds its own trouble, bending and scattering light as it passes through layers of air with different temperatures and densities. Clouds can block a beam outright. That means you need new kinds of ground terminals that can steer rapidly, compensate for atmospheric distortion, and hand off between sites when weather moves in. To get around some of these problems, future networks will likely combine radio and optical links. Radio waves punch through clouds and can serve as a robust fallback. Laser links can be used when skies are clear to shovel data at high rates. You can imagine an interplanetary internet where orbiters around Mars talk to surface robots using radio, then relay the heavy science data to Earth through lasers when the geometry and weather cooperate. Above, satellites with crosslinks form a mesh, passing packets of information around planets, moons, and stations the way terrestrial fibre networks route traffic today. The impact of such a network goes beyond making pretty pictures download faster. Higher bandwidth means scientists can think differently about what data to collect. Instead of carefully choosing a few hundred narrow spectra or a handful of high-resolution panoramas, instruments could gather continuous video, three-dimensional maps, and real-time environmental readings. A geologist on Earth might guide a rover with a sense of presence that feels more like telepresence than delayed email. Climate scientists could watch storms on Mars evolve in near real time. Engineers could diagnose problems with a robot as if they were standing next to it. For crews on long missions, communication is not just a technical need, it is a psychological lifeline. Astronauts on the International Space Station already rely on high-quality links to talk to family, watch news, and even do live events with classrooms. Extend that expectation to a crew heading for Mars, and the stakes rise. They will want reliable video calls, streaming medical data for doctors on Earth, and access to training materials and entertainment to fight monotony. A high-bandwidth, low-latency link can mean the difference between feeling like you are part of Earth with a long commute and feeling like you have been exiled to a tiny metal island in a cosmic sea. There are risks hidden in this dependence. A powerful solar storm can disrupt radio and optical links. Spacecraft and ground stations can be shaken by electromagnetic noise. In theory, networks can be hacked or jammed. That means building redundancy into the system, with multiple paths, backup antennas, and autonomous modes where a ship or base can take care of itself if cut off. Redundancy adds complexity and cost, but without it, a single failure could isolate a whole mission at the worst possible moment. As we imagine these networks, it is worth pausing and asking yourself a simple question. Who will own and operate this interplanetary internet? Today, the Deep Space Network is run by a public agency. In the future, private companies may build their own relay constellations around Mars or the Moon, renting bandwidth to whoever can pay. Nations may insist on their own secure channels. There could be debates over prioritizing commercial traffic versus scientific data, or over rules for emergency access. The arguments we have now about undersea cables and satellite internet coverage will follow us outward, just stretched across more emptiness. If you fast forward in your mind a few decades, you can start to see the outlines. A teenager puts on a headset and steps into a virtual representation of a Martian canyon in real time, walking along behind a rover as it drives, the images streaming across space and back. A surgeon in one country supervises a robotic operation on a remote outpost, her instructions encoded into laser beams that flicker between worlds. An engineer in a field office checks the status of a mining rig on the Moon on a tablet, only half aware that the data path to that rig passed through multiple nodes circling Earth and lunar orbit. All of that depends on us solving the quiet problem of how to listen and talk across the void. Not once, not as a heroic one-off, but as a routine service that just works. Once that invisible nervous system is in place, something else becomes possible. You no longer need every robot to see Earth directly. Machines can talk to each other, form local swarms, and report back as a group. Instead of one lonely rover crawling across a crater floor, imagine a pack of explorers, some on wheels, some on legs, some flying, all sharing data over a local network that only occasionally reaches home. When that day comes, the most interesting discoveries on other worlds may be made by robots we never see directly at all, working together in places no human has ever walked, underground, in ice, or inside ancient lava tubes. When those swarms finally fan out through alien lava tubes and buried ice caverns, they will be stepping into some of the most valuable real estate in the solar system. Caves on Mars and the Moon are not just spooky backdrops for science fiction, they are time capsules and potential shelters in one. Inside their walls is untouched geology that has never seen the abrasive wind of a Martian dust storm, or the harsh radiation that scrubs away delicate chemistry on the surface. If life ever clung on in a protected pocket underground, this is where traces might still hide. And if humans are ever going to live off-world in any serious way, this is where we will probably build our first real neighborhoods. To see why we need new kinds of robots for that job, it helps to think about the explorers we already have on Mars. Spirit, Opportunity, Curiosity, Perseverance, and the Chinese rover Zhurong all share the same basic body plan. 6 big wheels, a solid rectangular body bristling with instruments, and a mast full of cameras. Wheels are great on broad plains and gentle slopes. A large body gives you room to carry drills, spectrometers, weather stations, and computer brains. This design has taken us through dried-up river deltas, across dunes, and into craters that were once lakes. It is the workhorse shape of Martian exploration. Wheels also have a dark side. Spirit found that out the hard way in 2009, when it bogged down in soft sand. The rover tried to free itself, spinning its wheels and digging in deeper, but the trap never let go. Engineers made the best of it, turning Spirit into a stationary science station for a while, but its wandering days were over. Opportunity had a similar scare in 2005, stuck for weeks before carefully planned wheel maneuvers freed it. Even when the ground is firm, slopes are a problem. Opportunity could only safely drive on inclines up to about 30 degrees. When it reached Endurance Crater early in its mission, the walls were filled with exposed rock that could answer big questions about past water. Going down meant risking a one-way trip. The team ultimately decided to roll the dice. Opportunity found what they were looking for and crawled back out, but that outcome was not guaranteed. On a flat plane, those limits are acceptable. In a cave or a collapsed lava tube, they are mission killers. Picture a tunnel floor littered with boulders, sudden steps, and deep pits, with sections that narrow unexpectedly. A 6-wheeled, 2-meter-wide rover, built like a small car, is not going to squeeze through those twists and turns. It will slip trying to cross loose scree. It will high center on rocks. It will hesitate at sharp drops that demand nimble footwork rather than slow climbing wheels. If we insist on sending only that type of machine underground, most of the subsurface world of Mars will stay out of reach. On Earth, a different approach has been maturing in robot labs. Instead of rolling, these machines walk. One famous example was a four-legged robot nicknamed Big Dog, built by Boston Dynamics as a kind of robotic pack animal. Videos of it show a boxy body perched on four jointed legs, trotting over mud, climbing slopes, and catching itself when shoved. It can handle powdery ground that would swallow wheels, and it can step over obstacles instead of needing to drive around them. Watching it recover when it slips feels unsettling, because the movement looks strangely like a living creature regaining its balance. From that lineage came a more compact and polished machine called Spot. At first glance, Spot looks like a small, headless mechanical dog, painted in bright colours for industrial work. It was designed to inspect factories, walk through construction sites, and venture into places too dangerous for humans, such as areas with heavy radiation or unstable debris. Spot can carry loads of about 14 kilograms, enough for cameras, sensors, or even small robotic arms. It climbs stairs, moves across rubble, and keeps walking even when the ground tilts or jolts beneath it. If it falls, it can flip itself back upright from almost any awkward pose. The raw speed difference alone tells you how different this is from a Mars rover. Traditional rovers crawl along at around 0.2 kilometers per hour on flat ground. Spot can move at around 5.8 kilometers per hour, a comfortable human walking or jogging pace. But speed is not its most important feature. The real magic lives in how it sees and decides. Spot carries multiple cameras that look in all directions. Its onboard computers stitch those views together into a three-dimensional model of the world around it. Instead of waiting for a human operator to plan every footstep, the robot looks ahead, identifies obstacles, and chooses a safe path on its own. That autonomy matters because of the signal delays we talked about earlier. You cannot drive a robot on Mars the way you drive a remote-control car in your living room. By the time you see that it is about to tip over, the event has already happened. With Spot-style robots, you do something different. You tell the machine where you want it to go, perhaps by dropping waypoints on a map, and then it figures out the details. If the floor drops away on one side, it shifts its weight and plants its feet. If it starts to fall, it whips its legs into a new stance to catch itself, almost like an animal. NASA's Jet Propulsion Laboratory saw the potential in that mix of agility and autonomy, and wondered what would happen if you gave it a brain optimized for exploration. They teamed up with Boston Dynamics and plugged Spot into an advanced decision-making system known as Nebula. In test sites on Earth that mimic Martian caves, these upgraded robots have been sent underground without human babysitting. They step into total darkness, sometimes through smoke or dust, with only their own sensors to guide them. As they walk, they build detailed three-dimensional maps of tunnels and chambers, tagging interesting features like unusual rock formations or suspiciously smooth surfaces that might hint at past water. The vision is not just one robot, but many, working as a pack. You could have a scouting unit whose main job is to move fast, scanning everything. Another unit might carry a high-resolution camera or a spectrometer to analyze minerals at points of interest. A third might haul ground-penetrating radar or a small drill. The robots talk to each other over a short-range network, sharing maps and target lists. When the scout flags something promising, it tells the specialist which route is clear. The specialist then threads through the maze to that spot, takes its measurements, and sends the results back out along the chain. From the surface, you see only the final products, a set of detailed maps and data layers, but underground, a whole robotic team is choreographing its moves. Why put that much effort into caves? Because on Mars and the Moon, these hollow spaces may be the most informative and hospitable places we can reach. In a cave, you get a cross-section of rock layers that would otherwise require drilling. That lets geologists read the history of a region more directly. They can see where lava once flowed, where water might have seeped, and where minerals deposited in quiet pools. Caves also shield whatever lies inside from the worst surface radiation. Any organic molecules, fossils, or even dormant microbes have a better chance of surviving there than on an exposed plain. NASA's Braille program, which studies extreme life on Earth, has even looked seriously at the idea that cave-like environments on Mars could preserve traces of bacteria. For future settlers, the shelter is even more attractive. Without a global magnetic field like Earth's, both Mars and the Moon are constantly hit by charged particles from space. On the surface, this means living under a steady drizzle of radiation that would force humans to spend most of their time under thick shielding. A lava tube gives you that shielding for free. Tens of meters of rock overhead can block a huge fraction of the incoming radiation. The cave walls also buffer temperature swings. On the Moon, the surface bakes in sunlight and then plunges into deep cold every 2 weeks. Inside a lava tube, the temperature can be far more stable. It is hard not to look at such a natural bunker and think of future underground streets and farms. The problem is that from orbit we can only see hints of these systems. A satellite image might show a skylight, a circular pit with a shadow so dark you can barely make out anything inside. That tells you there is a void below, but not how deep it is or how far it extends. The floors could be smooth or jagged. There could be side passages, dead ends or sudden drop-offs. It is a bit like trying to plan a city by studying only the cracks in the roof. We need explorers that can go inside, map the interior, and come back out with a trustworthy picture. Send a traditional rover into that opening and you run into problems fast. The entry slope might be steeper than it can handle. The tunnel might narrow below the width of its body. Worst of all, as soon as enough rock sits between the rover and the sky, radio contact with Earth or an orbiter will vanish. That is acceptable for a brief period if the rover is following a script, but not for the kind of free-form exploration we need. A cave explorer on Mars has to be able to go in blind, make its own choices about which branch to take, and then find its way back out, all without live instructions from human controllers. This is exactly the kind of challenge that a competition called the Subterranean Challenge, run by the United States Defense Advanced Research Projects Agency, set out to simulate. NASA's Jet Propulsion Laboratory, Boston Dynamics, and academic partners joined forces as a team known as CoStar. Their task was to send mixed groups of robots into a series of test environments that included tunnels, natural caves, and mock underground urban spaces. Inside those dark arenas, the machines had to map the layout and automatically find objects that stood in for lost workers, equipment, or points of interest, then report their locations accurately. For Mars and lunar missions, the stakes are different, but the skills are the same. If robots can navigate collapsed mines and subway systems on Earth with minimal guidance, they can one day navigate lava tubes on Mars. The Subterranean Challenge Finals, held in 2021, were therefore more than a contest. They were a rehearsal for a future mission profile. You can almost imagine the same pack of machines, their industrial yellow plates traded for dust-stained white, marching down a ramp extending from a lander into the mouth of a Martian skylight, their cameras switching to infrared as daylight fades behind them. Once that type of system works reliably, a new style of space mission opens up. Picture a launch where the main payload is not a single hero rover, but a dozen smaller walkers packed tightly together. After landing near a cluster of skylights, the lander unfolds ramps and releases them like a kennel opening at dawn. Some stay on the surface, acting as communication relays and weather stations. Others head directly for the nearest entrance and begin descent. From Earth, we might see nothing more than slowly updating maps and data streams. On the ground, in darkness no human eye has ever experienced, small feet are stepping lightly over stones that have waited untouched for billions of years. These scouts would not just satisfy curiosity, they would be the first surveyors for construction crews that do not yet exist. Before we decide to build a base inside a given tube, we will need to know whether the roof is stable, whether there are hidden shafts that could dump rocks onto habitats, and whether there is accessible ice or useful minerals nearby. Legged robots with good autonomy can tap the walls with instruments to listen for hollow spaces, measure radiation levels along every meter of a passage, and spot any subtle shifts or tiny rock falls over time. In a sense, they become our long-term tenants in these caves, living there seasons or years before the first humans arrive. There is a strange symmetry here with science fiction. In H.G. Wells's story of invasion, Mars sends towering machines to Earth to conquer it. In our real timeline, we are quietly building small machines to send to Mars, not to conquer, but to make living there less deadly. Yet the presence of autonomous walkers on another world will still change the balance of power in a more subtle way. Whoever controls the best robotic scouts will find and claim the safest caves first, the richest ice deposits, the most stable ground. You can think of them as the pickaxes and survey flags of a new era, only with titanium legs and LiDAR sensors. As you imagine that, it is worth asking yourself how comfortable you feel sharing so much responsibility with machines. These robots will decide where to step, when to retreat, and what to flag as dangerous, often without any human watching in real time. Each choice they make shapes where we can safely build and where we dare not. Are they just tools, like clever shovels, or are they something closer to partners in exploration, a new kind of non-human explorer whose instincts we have to learn to trust? Our relationship with them will evolve as their skills grow. What is clear is that this partnership is not optional if we want to move beyond footprints and flags. The terrain ahead is too complex, and the time delays too long for old styles of control. The only realistic path forward is a layered one, where humans set overall goals and constraints, networks carry high-level plans and data, and local robotic teams improvise on the ground. Once that system is in place, caves become more than scientific curiosities. They turn into the skeleton of future cities, mapped and tested before any habitat is inflated or any airlock cycles. But mapping and scouting only solve the first part of the problem. Even with perfect three-dimensional maps of caves and lava tubes, we still face two cruel realities. The rock around those tunnels is still airless and dry, and the human body is still built for Earth. To turn a cold hollow into a place where people can sleep, work, and raise children, we will need ways to build walls out of dust, pull breathable air and water from alien chemistry, and keep our minds and muscles healthy in gravity that is weaker than we evolved for. And that is where the story turns from agile robotic paws on rock to heavy-duty construction systems and life support architectures that have to run for years without a pause. The moment you decide to turn a cave or a crater lip into a home, the questions get brutally practical. Where do you land so your ship does not crash in crosswinds or soft dust? Where do you park so that your solar panels see enough sunlight and your radiators can dump heat? How close do you dare to touch down near a skylight without risking damage from flying debris? You have to think like a pilot, an engineer, and a survivalist all at once. The maps that orbiters have drawn over the last decades suddenly stop being pretty pictures and become something closer to real estate listings. If you chase water, the poles call to you first. Radar soundings and neutron measurements suggest thick slabs of ice buried under soil in some polar regions on Mars. That ice means drinking water, oxygen, and rocket fuel if you have the right machinery. It also means long cold winters, powdered carbon dioxide frost, and sunlight that skims low on the horizon and disappears for months. Solar power in those latitudes becomes a seasonal gamble, and the extreme cold makes machinery brittle and stubborn. Move closer to the equator, and the trade-off flips. You get more consistent sunlight and milder temperature swings. Some equatorial or mid-latitude sites still hide buried ice, but the deposits are patchier and deeper. Landing is easier, surface winds are better understood. You can spread out solar farms without the sun dropping below the horizon for weeks. On the other hand, you may have to dig deeper or haul ice from shaded craters to feed your life support systems. Every kilometre you move from a resource source adds cost, complexity, and risk. In practice, mission planners talk about compromise zones, not the warmest place, not the iciest place, but regions where orbiters see clues of near-surface ice, where slopes are gentle enough for landings, and where the landscape offers some natural protection. A shallow crater rim can shield against horizontal radiation and micrometeorites. A nearby lava tube skylight might offer access to underground shelter later. You might imagine yourself as a future settler, scrolling through a list of candidate sites, weighing a description that reads safe landing ellipse, possible buried ice, moderate climate. Somewhere on that list will be the patch of ground where your grandchildren might take their first steps. Once the coordinates are chosen, the first structures to arrive may not have humans inside. Automated cargo ships and construction robots can be sent ahead on earlier windows, landing stacks of habitat modules, power systems, and excavation machines. In one popular vision, bulky inflatable habitats arrive tightly folded, and robots drag them to prepared pads before triggering inflation. The walls of these structures are multi-layered fabrics and composites designed to hold pressure, block small debris, and insulate against heat loss. Left bare on the surface, they would still be exposed to radiation and micrometeorite strikes, so the next step is to bury them. That is where Martian soil stops being just dust and becomes a building material. Regolith, the loose rock and sand that covers much of the planet, can be piled onto habitats with dozer blades and bucket wheels. A couple of meters of material on top cuts radiation significantly and helps smooth out daily temperature swings. More ambitious schemes use three-dimensional printing concepts. You mix regolith with binders, heat, or sintering beams and lay it down layer by layer, forming arches and shells around inflatable cores. The result is something like a stone building grown by robots, tailored to the exact stresses and shapes you need. Working underground is another path. If a lava tube is stable, robots could seal sections with bulkheads and airlocks, patching cracks and smoothing floors. Inflatable habitats could line the interior, turning portions of the tube into pressurized streets and rooms. The rock above acts as a natural shield and structural support. The downside is the effort needed to survey the tube thoroughly, repair unknown weak spots, and route power and communication lines into the depths. It is one thing to daydream about a city under an ancient Martian ceiling. It is another to bring in air ducts, sewage lines, lighting, and escape routes that meet real safety standards. All of these structures are shells. Inside them, the true heart of a settlement pulses quietly in the form of life support systems. On Mars, the atmosphere is mostly carbon dioxide, with only a thin sprinkling of other gases and almost no oxygen. You cannot simply filter it and breathe. You need machines that tear molecules apart and rearrange them. One family of devices uses electricity and catalysts to split carbon dioxide into carbon monoxide and oxygen. Another process combines carbon dioxide with hydrogen to make water and methane, a fuel, while freeing up oxygen. These reactions have been tested in laboratories and even on small scales on robotic missions, but running them continuously to support a town is another level entirely. Water may come from melted ice, chemically bound water in mineral grains, or recycled wastewater from the habitat. That water must cycle endlessly through filters, biological systems, and chemical beds. Every shower, every flushed toilet, every load of laundry becomes feedstock for the next glass of drinking water. On the International Space Station, astronauts already drink water that has been through this kind of closed loop many times. Extending that to a community on Mars means building redundancy into pumps, filters, and valves, and stocking spares for components that will inevitably fail. Every leak is not just a maintenance issue, it is a loss from an inventory that is hard to replace. Air is similarly precious. You want oxygen levels comfortable, and carbon dioxide below thresholds that cause headaches and impaired thinking. In a sealed environment, a patch of mold or a slow chemical reaction might upset that balance. So you watch sensors constantly and design systems that can scrub carbon dioxide chemically or biologically. Plants help, but they cannot be the only solution for a large habitat, especially in early phases. Chemical scrubbers, metal oxides that grab carbon dioxide and later release it under heat, become workhorse components. You may find yourself learning to appreciate the quiet hum of a fan as something more than background noise. It is the sound of circulation, of gases mixing, of life. Power hangs over all of this. Without electricity, pumps stop, heaters go cold, lights fade, and communications die. On the surface of Mars, solar power is the most obvious choice. The planet receives less sunlight than Earth, but still enough to run solar arrays. Panels can be mounted on fixed frames or on tracking systems that follow the sun across the sky. Dust is the enemy. Fine particles lifted by winds and storms settle on surfaces, slowly cutting output. You can picture crews or robots regularly sweeping panels or automated brushes gliding back and forth like robotic window cleaners. Then there are the big storms that envelop much of the planet in reddish haze. During those events, sunlight at ground level can drop dramatically for weeks. A settlement that relies only on solar will need significant energy storage. Batteries and flywheels can cover short gaps. For longer storms, chemical storage in the form of extra fuel or backup nuclear units becomes important. That is why some mission architectures lean heavily on small nuclear reactors. A compact fission reactor can sit in a shielded pit away from the main habitat and deliver steady power day and night for years. That steadiness simplifies life support planning, though it brings challenges in terms of launch safety and international politics. Once you have air, water, and power, the next question is what your settlers will eat. At first, most food will come from Earth, packed in dehydrated or vacuum-sealed form. That is not a long-term solution. To support a larger population and reduce resupply costs, you need local agriculture. Martian regolith is not soil in any comfortable sense. It is ground-up rock laced with salts and compounds that can be toxic to plants. Experiments on Earth using simulated regolith find that plants can grow if you wash out harmful components, mix in organic matter, and manage nutrients carefully. It is farm work, but with chemistry homework attached to every shovel of dirt. Hydroponics and aeroponics avoid some of those problems by cutting out soil entirely. In hydroponic setups, plant roots dangle in carefully oxygenated nutrient solutions. In aeroponics, roots hang in mist. Both methods allow fine control over nutrients and use water efficiently, which is crucial on a dry world. Rows of lettuce, tomatoes, and herbs can thrive under LED lighting tuned to plant-friendly wavelengths. Tubers like potatoes can be stacked in tall towers. Fish tanks can link into the system, their waste feeding plants in an aquaponic loop. The hum of pumps and gurgle of water in such a farm might become one of the most soothing sounds on Mars. Growing food is about more than calories. Fresh greens and bright colours help morale. The act of tending plants, watching tiny seeds turn into edible leaves and fruits, gives people a sense of connection and control. In a landscape of red dust and machine noise, a greenhouse becomes a small pocket of Earth-like sensory experience. The smell of damp leaves and soil substitutes, the sight of condensation beading on transparent panels, the routine of pruning and harvesting, all anchor the mind. In confinement studies on Earth, people often report that looking after plants helps them cope. You can expect the same to be true tens of millions of kilometers away. None of this makes the human factor easy. Even if the air stays breathable and the lights stay on, the mind has to adapt to a world where a walk outside means hours of preparation and a constant background risk. The view out of a window is not a forest or city street, but a rocky plain under a salmon-coloured sky. The knowledge that home is months away by rocket, with launch windows that only open every couple of years, can be both inspiring and crushing. Some will see the distance as freedom, a chance to build new norms. Others will feel it as isolation every time a connection drops in the middle of a call. Living in reduced gravity adds another layer of stress. On Mars, you weigh about 1/3 of what you do on Earth. At first, that will feel delightful, a constant bounce in your step, heavy loads suddenly manageable. Over years, doctors worry that muscles and bones will slowly adjust downward. On the International Space Station, where astronauts float weightlessly, exercise regimens and medication help manage bone loss. On Mars, the gravity is not zero, but we do not yet know whether it is enough to keep the skeleton and cardiovascular system healthy over decades. Maybe treadmills with harnesses, centrifuges in recreation rooms, and targeted drugs will be enough. Maybe they will not. Social dynamics will be under a microscope. Early crews will be small, maybe a few dozen people at most. In such a small group, every personality looms large. Conflicts that could be shrugged off in a city might simmer dangerously in a sealed habitat where you cannot get away. Selection processes will have to weigh not just technical skills, but emotional resilience and the ability to live in close quarters without escalating every disagreement. Even then, relationships will form and break, cliques will arise, and the usual human dramas will play out, only with nowhere to storm off to when tempers flare. Psychologists talk about phenomena like the third quarter effect, where people in isolated missions often find mood and performance dipping after the halfway point, when novelty has worn off, but the end is not yet close. A crew on Mars might experience something similar stretched over years, feeling both the weight of routine and the weight of responsibility, as they realise there is no backup crew arriving in days if they falter. You can picture shared movie nights, game tournaments, and simulated trips back to Earth through virtual reality, all tools to keep a fragile social fabric from fraying. Add to this the reality that children may one day be born and grow up in that gravity, in that sealed environment. Their bones and hearts will develop in a world with different loads. Their sense of normal will be a pressure door and a dusty horizon, not an open sky. Are they visitors to Mars or natives? Would they ever even want to come to a world where walking feels like moving through syrup compared to the light steps they know? These are not questions you can answer with engineering charts alone. So when we talk about building a home on Mars, what we really mean is building an entire system that can keep human life stable in a place where it has never existed before, and doing so in a way that feels worth living, not just worth surviving. Robots will scout caves and stack bricks of regolith. Reactors and panels will hum. Greenhouses will glow softly in artificial dawns. And around all of that, men, women and children will try to stitch a culture out of red dust and memories of a blue planet they may visit only in dreams. At some point, the tools we build to protect those fragile bodies and minds may start to look less like shelters and more like the first hints of something deeper. A willingness to change ourselves as radically as we are changing the world around us. Once you start thinking seriously about changing the human body to survive elsewhere, another thought creeps in. Maybe there is a gentler path, one where we change the landscape we visit, rather than rewriting ourselves completely. Before we talk about altering genes or reshaping bones, there is a closer, colder place where we can practice something simpler and yet just as transformative. Turning a dead world into a supply yard. For that, you do not begin on Mars. You begin with the grey companion that has been hanging in our sky since before we had words for it. The moon looks barren, but from a resource standpoint it is less empty than it appears. Its surface is covered in regolith, a blanket of shattered rock made by billions of years of meteorite impacts. That dust is abrasive and clingy, terrible for spacesuits and machinery, but it hides useful ingredients. Oxygen is locked up in oxides of silicon, iron, and other metals. Hydrogen and water ice seem to lurk in permanently shadowed craters near the poles, where sunlight never reaches and temperatures stay low enough for ice to survive for eons. Scattered through the mix are elements like titanium and aluminum. To a geologist, these are clues to formation. To an engineer, they are a catalogue of potential raw materials. Extracting them is not as simple as scooping dirt into bags. Oxygen bound in minerals does not come free without energy. One proposed method is to heat regolith in the presence of hydrogen or other reagents so that oxygen joins the gas and leaves metal behind. Another is to melt regolith in molten salt and pass electric current through it, separating elements the way smelters do on Earth. The hardware to do this would be heavy and complex, but once running it could turn local dust into air, metal and slag. In one stroke, a place that looked like a desert becomes a quarry and an air plant. Water ice near the poles is even more strategically important. Break water into hydrogen and oxygen, and you have two of the main ingredients of rocket fuel. Liquefy them, and you have propellant. A tanker refilling near the lunar poles could top off tanks without hauling every kilogram up from Earth. From there, the path to other worlds gets easier. The cost to climb out of the moon's gravity well is lower than from Earth, and there is no thick atmosphere to plough through. If we can build reliable depots in space stocked with lunar propellant, Mars and the outer planets stop being distant targets for rare missions and start to look like stops on a logistics route. You can imagine a future map of space with waypoints the way old sea charts had coaling stations. Earth to low orbit on one leg, low orbit to a fuel stop near the moon on another, then outward to Mars or asteroids. At each step, ships arrive mostly empty, refuel, and continue. The idea sounds elegant on paper. In reality, it requires an entire industrial chain on and around the moon. Mining machines that can operate in a vacuum and in deep shadows. refineries that can survive lunar nights that last 2 Earth weeks, tanks and plumbing that can handle cryogenic liquids without bleeding away your profit as boil-off. That is before we even touch the most headline-friendly possibility, the presence of helium-3 in lunar soil. Helium-3 is a rare isotope of helium with 2 protons and 1 neutron. Fusion researchers have long talked about it because certain theoretical fusion reactions using helium-3 could produce energy without spewing out as many high-energy neutrons, in theory leading to cleaner reactors and less activation of surrounding materials. Over billions of years, the solar wind has sprinkled helium-3 onto the lunar surface, where it becomes trapped in regolith grains. That has led to bold statements about mining helium-3 on the Moon as a way to fuel a future fusion-powered civilization on Earth. The reality is more sobering. Helium-3 is indeed present in lunar soil, but in very low concentrations. To gather even modest amounts, you would need to process vast volumes of regolith, heating each kilogram enough to drive out the trapped gas. The machinery to do that at scale would be immense. You would also need working fusion reactors on Earth that actually use helium-3 fuels efficiently, which we do not yet have. So when you hear someone pitch helium-3 as a near-term lunar gold rush, it is worth holding that thought up to the light. The physics does not rule it out. The engineering and economics make it a long bet rather than a guaranteed prize. More grounded in the near term are metals and rare earth elements. Despite the name, rare earths are not scarce in an absolute sense, but they are hard to concentrate and refine cleanly on Earth without environmental damage. They underpin much of modern technology, from magnets in wind turbines to components in smartphones. Some regions on Earth currently dominate their production, which gives them leverage in global supply chains. If the Moon holds concentrations of such elements that are easier to exploit under loose environmental rules, there will be strong pressure to dig. A mine on the far side of the Moon does not release tailings into a river where children drink. It dumps waste onto empty plains. That feels morally different at first glance, until you remember that dust and debris in low gravity do not always stay put. Some will become orbiting hazards, or drift into boundless space. You might feel a tug of conflicting instincts here. On one hand, moving heavy industry off Earth sounds like a win. Our homeworld is already under strain from extraction, pollution, and climate change. If we can shift some of the dirtiest work to a lifeless rock, perhaps oceans and forests will have a better chance to recover. On the other hand, extending our habit of treating some regions as sacrifice zones into space raises uncomfortable questions. Are we exporting exploitation rather than ending it? Who gets to decide which crater becomes a strip mine and which remains untouched as a scientific preserve? Money and power will shape those answers as much as ethics. Companies that invest early in lunar infrastructure will want returns. Launch providers will see steady business hauling equipment, people, and refined materials. Nations will see influence in the form of supply control. Control over copper or oil shaped global politics in the last century. Control over access to energy storage materials, satellite construction metals, and high-end electronics components could shape the next. Lunar regolith might not look like a weapon, but access to its products could become leverage. All of this would be complex enough if space law were clear. It is not. The core principles in place today were written in an era when only states went to space, and the fear was that one superpower would plant a flag and claim the Moon as territory. The foundational treaty says that no nation can claim sovereignty over a celestial body. It encourages the free exploration and use of space by all countries. It treats space as the province of all humankind. Yet the same text leaves room for different interpretations about resources. Some legal scholars argue that while you cannot own the Moon itself, you can own materials you extract, the way you can fish in international waters and claim the catch. Others argue that large-scale industrial use risks violating the spirit of shared heritage. In recent years, a few countries have passed national laws that explicitly grant their companies rights to resources they obtain in space, framing these as property rights similar to mineral claims. Other countries object, either on philosophical grounds or out of concern that they will be left behind, while early movers carve up the most accessible deposits. This tension is not only about laws on paper, It is about who gets to write norms through action. If the first permanent lunar base is run by a small consortium of companies and agencies that set their own rules, their decisions will define what feels normal. Do they charge refueling fees in ways that lock out competitors? Do they share mapping data about resources freely or treat it as proprietary? Do they agree to keep certain polar craters untouched because they preserve records of ancient solar history? Or is every feature for sale if it can turn a profit? Think about traffic too. A fully industrialized moon would need constant shipments of equipment, spare parts, and people. That means more launches from Earth, more landers touching down in delicate dust environments, and more risk of contamination of sites we currently value for pristine science. Astronomers dream of placing radio telescopes on the far side of the moon, shielded from Earth's noise. Mining vehicles nearby could threaten that quiet. Dust plumes kicked up by frequent landings could coat optics and solar panels that were meant to operate for decades. For future settlers, a lunar mine could be both opportunity and threat. Jobs, infrastructure and power sources make longer stays possible. At the same time, living next to heavy machinery in low gravity carries hazards. Outgassing, dust mitigation, and noise become quality of life issues. The image of a silent crater lit only by stars shifts to one of conveyor belts, excavators, and lights washing over regolith hills. Whether that feels like progress or desecration depends on your values. One thing seems likely. The first serious fights over extraterrestrial resources will not be about Mars or far-flung asteroids. They will be about this close world that swings past our windows every month. It is reachable with current or near-term rockets. Its gravity is strong enough to hold structures and equipment, but weak enough to make moving mass around relatively cheap. It sits in the sweet spot where investment might pay off within a human career. That is why plans for lunar exploration over the next few decades often talk explicitly about resource surveys, pilot extraction plants, and demonstration refineries. It is worth asking where you think the line should be drawn. Is it acceptable to strip mine a small region of the moon, if doing so allows thousands of coal plants on Earth to shut down sooner? Should there be protected zones where no industrial activity is allowed, analogous to national parks or World Heritage sites? Who decides? Do we need a new treaty, or can we bend the old ones? These questions may sound abstract, but the hardware that will force real answers is already being designed. The strange part is that this resource rush will coexist with pure science in a messy overlap. A robotic lander sent to prospect for ice might also carry instruments to study the history of the solar wind recorded in regolith grains. A telescope farm on the far side might share its power infrastructure with a radio relay owned by a private company. The same crater rim that makes a beautiful panoramic shot of Earth hanging in a black sky may later sprout towers and domes that blur the line between observatory and industrial site. As this plays out, the moon risks becoming a mirror for our priorities. If we rush to extract, build, and profit without thought, we will recreate many of our worst habits on a new stage. If we move more deliberately, using the relative emptiness of the lunar surface as a testing ground for sustainable practice, we might learn how to expand our civilization without always leaving scars that last for ages. Standing on that knife edge, it is not enough to ask what we can dig up. We have to decide what kind of spacefaring species we want to be. The choices made in the cold light of lunar dawn will ripple outward. A legal framework that favours a handful of actors at the poles may lock in economic advantages that extend to Mars and beyond. A norm of sharing certain kinds of data could accelerate science everywhere. A norm of secrecy and restrictive licensing could slow exploration for those outside elite groups. The maps our grandchildren study might show trade lanes and resource hubs stamped with corporate logos as familiar as national flags once were. And all of this unfolds against the backdrop of something deeper we have only begun to touch. While we argue over who owns which crater and which ice deposit, our tools back on Earth are quietly advancing toward the point where we can modify the explorers themselves, not just their surroundings. We are learning to tweak genomes, nudge cells to resist radiation, and design life that might thrive in places no human has ever stood. The next chapter does not just involve using the moon as a mine, It involves deciding how far we are willing to go in changing the human template for the sake of reaching and using these new frontiers. The tools we build to tame harsh worlds always reflect the bodies we bring with us. On the Moon and Mars, we talk about armor, shielding, buried habitats, clever materials that keep fragile human cells out of danger. That approach treats the human body as fixed and the universe as hostile scenery to be padded and insulated. But in labs back on Earth, another idea is taking shape, stranger and more unsettling. Instead of wrapping the same old body in thicker walls, what if we made the body itself a little more at home in the places we want to go? At what point does exploration stop being about travel and start being about self-redesign? Start with the problem that will not cooperate no matter how well we engineer our ships: radiation. Between worlds, charged particles from the sun and from distant cosmic accelerators rain through metal and plastic. On Earth, our atmosphere and magnetic field take most of the hit so quietly you never notice. In deep space, that shield is gone. Every mission plan you have heard about Mars or beyond must wrestle with this limiting cold numbers, balancing travel time, shielding mass, cancer risk, and mission value. You can shorten the trip with better engines and tuck habitats into caves, but unless we discover some truly exotic form of protection, the radiation is always there, nibbling at DNA. NASA's twin study hinted at just how deeply space can write itself into our biology. One twin spent almost a year on the International Space Station, the other stayed on Earth. Their genes began identical. After the mission, scientists compared patterns of gene activity, the switches that tell cells which instructions to read. They saw immune system changes, shifts in the way DNA packaged itself, and tiny differences in the length of chromosome end caps that help govern cellular aging. Most of those effects faded with time back on Earth, but some persisted longer than expected. The lesson was clear. Space does not pass through us like weather. It leaves fingerprints at the level of our molecular wiring. If you are an engineer, one way to respond is to add more aluminium and water tanks. If you are a biologist, your mind eventually lands on a different question. Out in nature, are there organisms that already shrug off radiation that would shred a human cell? The answer is yes. Tough little animals called tardigrades can survive blasts of X-rays that would be instantly lethal to us. Certain bacteria and fungi keep repairing their DNA even after heavy damage. For years, these creatures were scientific curiosities, front-page weirdos that could live in boiling water or frozen rocks. Now they look more like libraries of tricks that evolution has already figured out. In the last decade, researchers began borrowing from that library. In one set of experiments, they took a gene from tardigrades that makes a protein nicknamed Dsup and inserted it into human cells in a dish. Those modified cells became noticeably more resistant to X-ray damage than their unedited cousins. Other teams have tinkered with yeast and bacteria, adding genes that help them tolerate radiation or desiccation. These are early studies, done under careful containment, with no intention of putting modified cells into a living person. Yet they demonstrate something profound. The line between fragile human tissue and radiation-hardy extremophile is not a wall. It is a series of biochemical choices that can be rewritten. Now add a tool that has transformed biology in less than a generation. A simple pair of molecular scissors guided by a short piece of code that can be aimed at almost any gene. CRISPR technology, as it is commonly called, lets scientists cut and modify DNA with a precision that would have seemed impossible a few decades ago. With that precision comes a rush of possibilities and ethical landmines. In 2018, news surfaced that a researcher in China had used such tools to alter the genomes of human embryos, which were then carried to term. The edits were meant to confer resistance to a virus. The world reacted with alarm and anger. Most of the scientific community condemned the work as reckless, premature, and deeply unethical. That incident crystallized a fear that had been simmering quietly. The same tools that can correct a defective gene in a child with a lethal inherited disease can also be aimed at traits that are not matters of life and death: height, metabolism, perhaps even aspects of cognition. Today, global guidelines draw a hard line. Editing somatic cells in an adult to treat disease is often accepted if done carefully. Editing embryos or reproductive cells that will pass changes down the generations is widely viewed as off-limits. The ground under that line may not stay still forever, especially if pressures build from places that see survival and expansion, not just health, at stake. Imagine you are sitting in a planning meeting for a long-duration colony on Mars, or for crews living in deep space stations for many years. The medical officer runs through radiation exposure estimates, bone density loss projections, cardiovascular stress curves. At some point, someone asks a question that hangs in the air. What if we could lower these risks, not only by tweaking the habitat, but by tweaking the people? Not to build mythical superhumans, but to nudge their biology so that bone loss slows, DNA repair speeds up, and the cardiovascular system tolerates low gravity better. Concrete ideas are already being sketched in conferences and papers. Editing stem cells so that new bone-forming cells are less likely to abandon their work in low gravity. Introducing protective proteins like Dsup in a way that is limited, reversible, and tightly controlled to give blood-forming tissues extra resilience. Adjusting the way red blood cells respond to low oxygen, inspired by high-altitude populations on Earth, to reduce stress when air supply margins are thin. None of this is trivial. Side effects and unintended consequences loom everywhere. Protecting DNA from damage without also protecting cancer cells from chemotherapy, for example, is a non-trivial balancing act. There is also the psychological dimension. How would it feel to volunteer for a mission that requires permanent genetic alteration? Would you feel upgraded, marked, or both? Would children born in an off-world colony inherit those changes as ordinary features, becoming a population whose physiology diverges gradually from Earth norms? At what point do we look at a long-established Mars community and say they are still us, just adapted, versus saying they are a branch of humanity that might one day look at Earth immigrants the way we once looked at visitors from another continent? While these debates unfold, a quieter kind of adaptation work is happening on a very different frontier that shares surprising similarities with space: the deep ocean. At depths of hundreds of meters, sunlight fades to blue twilight. Go deeper, and even that glow vanishes. Pressure climbs to levels that would crush unprotected human lungs and sinuses instantly. Communication is limited. Rescue options are slim. It is no accident that NASA has used underwater bases as analogues for space stations and planetary habitats. Off the coast of Florida, there is a small structure bolted to the seafloor called Aquarius. It looks like a metal cylinder with portholes perched on stilts. To reach it, aquanauts must dive down and swim through a kind of wet front door, entering a pressurized interior where the air is at the same pressure as the surrounding water. Once inside, they live in a sealed environment for days or weeks, venturing out in dive gear for long excursions and then returning without needing to surface. Because their bodies equilibrate to the high pressure, they cannot simply pop back to the surface whenever they wish. They must undergo careful decompression to avoid injury. NASA has run a series of missions called NEEMO, using Aquarius as a space analogue. Astronauts and researchers live in the habitat as if it were a small outpost on Mars or an asteroid. They practice delayed communication with the control center on land, simulate spacewalks by climbing over rocks in heavy suits, and test tools in a place where the environment is unforgiving and isolation is real. Living in Aquarius feels different from living on the International Space Station, yet many of the psychological challenges rhyme. Confined quarters, a small crew, no easy escape if something goes wrong. The experiments there help refine everything from checklists to group dynamics. Beyond such human-occupied habitats, robots dominate the deep. Remotely operated vehicles dangle from ships on cables, their cameras sending back ghostly footage of black smokers and strange bioluminescent animals. Autonomous underwater vehicles roam on their own, mapping the seabed with sonar, taking samples, and returning when their batteries run low. One of these, called Nereus, once dove to the deepest known ocean trench, surviving pressures thousands of times greater than at sea level. Another, named Orpheus, is being developed with an eye toward exploring not only our own Hadal trenches, but also serving as a template for missions to ice-covered moons. When planetary scientists talk about Europa, a moon of Jupiter, or Enceladus, a moon of Saturn, their voices often carry an excitement that is hard to miss. Both worlds appear to have thick shells of ice over global oceans of liquid water. On Enceladus, that ocean vents through fissures near the South Pole, sending plumes of water vapour and icy particles spraying into space. A passing spacecraft has already flown through those plumes, tasting salts and organic molecules. On Europa, the ice surface is cracked and ridged, hinting at tides and currents below. For anyone who cares about life beyond Earth, these are not just interesting rocks, they are possible abodes. To explore those oceans, you need a machine that can do several very hard things. It must land on an icy surface far from the sun, drill or melt its way through kilometers of frozen crust without contaminating what lies below, then release a submersible that can navigate in complete darkness under crushing pressure, all while sending its findings back through that same borehole to a relay on the surface. The best rehearsal space for that is not a lab bench, it is the deep ocean of our own planet. Every test dive that sends Orpheus or a similar vehicle into a black, cold trench is effectively a dress rehearsal for a future dive into alien water. You might notice how the themes begin to overlap. On Mars and the Moon, we talk about caves and lava tubes as shelter and scientific treasure. In the outer solar system, we talk about ice-covered oceans as potential cradles for life. In both cases, robots go first. They map, measure, and send back data. Behind them, humans on Earth tinker with genetic tools and medical regimes that might someday let our descendants walk more comfortably under weaker gravity, or tolerate long periods away from sunlight. Between these efforts runs a shared thread. We are learning to treat harsh environments not as absolute barriers, but as conditions to be managed, engineered around, and maybe even engineered into ourselves. There is a danger in that mindset that is worth stating plainly. Power to alter environments and genomes does not come with built-in wisdom. Planetary protection rules already try to limit contamination of other worlds with Earth life, for fear of erasing native biosignatures before we can even recognize them. As bioengineering becomes easier, there may be temptations to seed hardy microbes deliberately into marginal niches in the name of terraforming, or to introduce engineered organisms into deep-sea ecosystems on Earth with promises of cleanup and carbon capture. Each such move carries risks that ripple for generations. The question is not only what we can survive, but what we are willing to change irreversibly. So picture a scene 100 years from now. A small team of explorers lives in a buried habitat on Mars, their bones and blood slightly different from yours, tuned by careful edits and medication to cope with low gravity and radiation. Above them, small-legged robots patrol the entrance to a lava tube that has been turned into farmland and storage. Far away, a silent probe hangs over the ice of Europa, its drill modules slowly boring downward, while a submersible waits within, its hull design a direct descendant of machines that once swam through Earth's deepest trenches. Data from both places streams back to Earth through a web of laser links and radio relays, feeding into laboratories where biologists compare Martian cave chemistry and European ocean samples with the strangest microbes in our own crust. In that world, the line between exploration and transformation will have blurred. Our machines will have gone where we cannot yet go, and returned with stories written in spectra and pressure curves. Our bodies may have been nudged slightly away from the blueprint that defined humanity for hundreds of thousands of years. Our ethics will have been stretched by choices about what to mine, what to protect, what to seed, and what to leave untouched. We will no longer be a species that simply lives under one sky and looks up. We will be a species that has begun to remake both its surroundings and itself to fit a wider, harsher cosmos. The question that remains for you and me is disarmingly simple. As we chase distant planets and hidden oceans, as we teach robots to walk in ancient caves, and teach cells to shrug off radiation, what do we want to keep unchanged at the core of the story? Is it our shared curiosity, our capacity for wonder, our stubborn refusal to treat any horizon as final? Or is it something deeper about how we treat one another while we pull new worlds within reach? Somewhere between the launch towers and the gene editors, between the deep-sea labs and the frozen moons, we will find out what kind of explorers we really are.